Hello, and welcome to the Stardog Academy training on modeling. This is Paraskevi Zerva, one of the solutions architects at Stardog. To let you know a bit more about me, I've been working for more than 10 years designing and modeling data architecture solutions with a keen interest in solving complex data problems in the areas of data integration, data governance, provenance, data quality, and data science, specializing on knowledge graph and graph database solutions across different data domains. So today I'm going to walk you through the foundational concepts and building a data model for your enterprise knowledge graph. So in this training session, you will learn fundamentals of data models and data modeling as a process, basics of existing types of models including ontology models, main steps of ontology model development process and associated best practices, foundational concepts of ontology models through showcasing examples and existing modeling standards and language representations. And by the end of the training, you will know how to start and build an ontology model using Stardog Studio. So let's get started. So our first introduction section is on fundamentals of modeling. What is the role of data modeling and data models in general? Data modeling is a process used to define and analyze data requirements within the scope of information systems. Modeling is also used as a technique for detailing business requirements for specific databases, and this is what we call database modeling in the relational database world. A data model organizes elements of data and standardizes how they relate to one another and to the properties of real-world entities. And it helps us to explicitly determine the structure of the data by providing specific definitions, while it also provides a way to formally represent the data structures or a set of concepts such as entities, attributes, and relations. There are different types of models, and one of these is also ontology models. So three perspectives exist on data model instances at different phases of the modeling process. So first of all, we have conceptual data model. This describes the what of a domain by scoping down the key concepts and rules of that domain. Then we have a logical model. This describes how key concepts and entities should be modeled and provides a technical map and model of the rules and the data structures. And then we have the physical model that basically describes the physical means and structure by which data are stored. There are also different types of models that exist out there. For example, in the relational world, a database model or schema forms a blueprint on how a database is constructed. Now, in the semantic or knowledge graph world, we use ontology models. An ontology model defines the set of concepts and relationships that represent the content and structure of the domain, while it also provides a strong focus on formal semantics. We will see more on that in the rest of the presentation. So, what are then the core concepts of the ontology model? An ontology defines a set of representational primitives with which to model a knowledge including classes, or else called sets or entities, then attributes, which are the relations between a class member and text data, such as date or string or a boolean or an integer, and then relationships, which are the relations among class members. We also have additional modeling tools such as axioms and rules, and this is used to define information about the meaning of the corresponding primitive concepts. And we also have constraints, and constraints, it's a modeling tool mainly used for validation. In the context of knowledge graphs, an ontology model forms a flexible schema designed to highlight the relationships between the concepts, and we actually represent this as a graph data structure. Ontologies are specified in languages that allow abstraction away from data structures, closer in expressive power to first-order logic. Therefore, we say that they are operating at semantic level. Stardog is based on the RDF open standard, the Resource Description Framework open standard, created to represent large-scale information systems. So to summarize, the W3C ontology language standards that we use and Stardog support is the Resource Description Framework language. So this is used to represent instance data. The rdfs schema, this is in order to represent class and property hierarchies. OWL standard, which is the OWL representation language that has a little bit more expressivity in the definition of our constructs and concepts. SERL language, which is a language for building rules and creating functions for these rules. And then SACL, which is the shapes constraint language used for defining validation rules. In the next section of this training, we're going to look in the model development process steps for an ontology model. So how to start the development of a model? No single right way exists to model a data domain. Capturing data requirements that emerge from business questions that need to be answered should be our first approach and priority. By building your model iteratively, you actually go through the process of identifying, as part of the data requirements captures, what are these key entities, attributes, and the relationships that are critical to your business requirements. Just follow simple ontology development guidelines by adding new entities and properties and relationships between these entities, and adopt usual software engineering practices, such as iteratively extending your ontology features and also testing your ontology. So let's say an example. Here we have a business question example taken from the music data dataset domain. And here is the question. Identify percentage of sales of most popular musical albums and music genres and categorize by date. Looking into this question and trying to analyze the data requirements in that, we identify the key entities here being album and music genre, and also important attributes around albums such as date and sales percentage. At last, we also identify relationships between album and music genre with the house music genre relationship identified. So let's look now what are the key ontology development steps. First of all, you need to determine the scope of the ontology by actually looking in your data requirements. Second, you should identify the core classes like critical entities. Third, we need to build the class hierarchy. And fourth, we need to specify properties. This could be relationships or attributes, ours called object and data type properties per the W3C standard terminology. So looking in the first step, let's try to determine the ontology scope. We should try to create a minimum viable product of the first version of our ontology. This is done by actually putting a minimal ontological commitment as much as possible. Overspecification hinders extensibility and may requires to go into the requirement for modularizing our ontology into smaller models. Try to generate some competency key questions and validate whether your ontology model is able to answer these questions. Determine that by looking into whether the ontology contains enough information by defining the required entities and property relationships. So in the second step of our development process for the model, we should try to specify core classes. These are representing our key entities, and also we should try to define the related properties and individuals. All of these definitions help us setting the scope and structure of our model. The reusing of terms is possible, and it's also recommended, but we should make sure that this provides some type of value that we can get from this vocabulary, while we make sure that the ontology model still is lightweight and we avoid to create issues that affect the performance of our knowledge graph or the query performance. At last, we should determine the types of terms. So let's look into more details about what kind of terms we can reuse and what kind of standard vocabularies exist out there. Resource Description Framework Schema, RDFS, defines terms such as rdfs label and rdfs comment, and we can use these terms to define labels for our concepts and classes and properties, but also provide notes and comments for them. Other standard ontologies, such as friend of friend ontology, is able to describe people and organizations and activities for them. Duplicate core metadata ontology allows us to define metadata about digital dogs. And other standard vocabularies and ontology exist, such as COS, defining structure of taxonomies and hierarchy relationships and control vocabularies, schema.org, good relations, and FIBO for financial services domain. Be aware of existing ontology standards and reuse this consciously based on what you're trying to achieve within your data model domain. So, we mentioned that as part of the ontology development process, we should define the types of terms. And it's important to do that and distinguish between classes versus relationships or object type properties, and classes versus individuals or instances. So let's see some examples. The term person here is defined as having a type class. And this allows us to say that a person denotes any individual that is a person. On the other hand, member of term is defined of the type relationship or object type property. And this basically denotes that a person can have a member of relationship to Music Bank, for example. Also, we have a distinction between class and individuals. And based on the context, we could have jazz music to be defined as a class and being a subclass of music gene, where in this case we talk about the class hierarchy. Well, in the context of jazz music being a type of thing, then we would say jazz music is an instance of music genre. So the third step in our ontology development process is the class hierarchy definition. This is the backbone of the ontology. It is important for the understandability of the model, but also for reasoning and inheritance. Subsumption relation is the inheritance of properties from the parent subsuming class to the child subsumed class. Anything true of a parent class is also going to be true for all its child classes. And in ontology models, we have two options. A class is allowed to have only one parent, and in this case, we talk about single inheritance, or it could have multiple parents, and in this case, we talk about multiple inheritance. Well, be principled but balance it with pragmatics. Follow common sense rules to define your class hierarchy and avoid deep philosophical debates. Just be practical. So let's see a class hierarchy example. In this example, by music data dataset, artist is defined as of type class, and in this class hierarchy, we have two subclasses, solo artist and band, that are both defined as subclasses of artist class. To give some hierarchy guidelines with regards to class hierarchy creation, we should add classes as needed. Subclasses should have different characteristics than the superclass. With regards to intermediate classes, a simple subclass denotes either incompleteness or redundancy, while too many subclasses denote that we might not have enough categories defined. In general, try to model consistently. Homogeneous symbolic subclasses should be part of the same hierarchy, while we should distinguish between part-whole relations versus subclasses. Part-whole relations denote composition, while subclasses denote inheritance. The last step of the ontology development process is the specification of properties. We should look which class should, can, must be used by which property. We distinguish between object and data type properties, as called relationships and attributes. For each property, we have to define the domain and its range, and we can have global definitions such as rdfs domain and rdfs range terms that apply to all instances of the property, but we could also have local definitions such as all some values from and all values from that constrain the range of a property in specific contexts by local restrictions to its class. In addition, SACL constraints for closed-word database schema and data validation can be used, but we can see more information and details on SACL constraints in the corresponding training. So we have covered a lot of ground. So let's summarize the main terms defined and the distinction between these. So classes refer to sets, collections, concepts, types of objects, and kinds of things. Properties refer to all types of object relationships or data type properties, as called attributes. Relationships refer to object properties based on the OWL RDF standard terminology, and attributes refer to data type properties, again based on the W3C, OWL, and RDF standard terminology. Individuals may also be called instances or objects. These are the basic or ground level objects defined in our model. And in terms of graph representation diagrams, classes and individuals correspond to nodes, while properties correspond to edges. Now, regarding the RDF tuple notation, if you have already followed with regards to the RDF and Sparkle training, classes and individuals could be used in the position of subject or object in the RDF tuple notation, while properties correspond to predicates. Now, if we put in practice a diagram representation example from the music data domain, as we can see, album and class, album and song are defined as classing in this example, where album has a relationship or object type property track with the class song, and also album has an attribute or data type property called date, where the range ranges to an XST data time value. Also, we define an instance or individual example of the class song, which is let it be. So in this section, we're going to discuss ontology concepts through example. As we have already mentioned, in order to start creating an ontology model, we should try to focus on creating a minimal viable product. Some basic modeling rules should be to start with 3 to 5 key concepts identification and their relationships, and then a little modeling can go a long way. Over-specification hinders reuse, and in some cases, defining too many new concepts and relationships that do not necessarily provide an added value to the data domain and the use case just add complexity to the model for no reason. You should try to layer your model and start simple and extend and refine definitions as you go. Naming should also reflect the real-world entities and relationships, as your model will be your lingua franca for your data domain. Also, the naming of concepts and relationships should match what domain experts say and think. If we take a look in the music data example, defining the music data domain, as we can see, there are some key ontological concepts defined here, such as album and song, an artist and songwriter as a number of classes, and then a number of relationships such as track and artist and writer that define relationships between the main classes or define attributes of the classes such as the date and the length of the song. In order to declare something that is of type class or that is of type property, we can use rdfs or OWL. rdfs, the Resource Description Framework schema notation, uses rdfs class term for defining classes, so we can say that an album is of type rdfs class. And for properties, it can use rdf property term, so we can say track is of type rdf property and the date it's of rdf property. So in both cases, both for object and data type properties, we use the term rdf property. Now in OWL notation, for defining classes, we use the term OWL class, so we can say an album is of type OWL class. And then for object and data properties, we can distinguish by using the terms OWL object property and OWL data type property correspondingly. Now, looking a little bit closer on the class and its notation of rdfs class, a class represents a set of individuals or instances or entities, as we have defined into our data requirements capturing, that have some common characteristics. As we can see in our music data example, an artist is defined as of a class type, and also classes can be organized in a hierarchy using the rdf subclass of term by resource description framework definition as well. So, as we can see in the music data example, solo artist and band are subclasses of artist. At the end, we have to say also that instances of such classes can be classified automatically under the hierarchy based on their properties. Another thing is that the main class of an ontology could be defined as of type OWL class or OWL thing as well. And these terms are both defined in the OWL language notation, and Stardog supports both of these. An important distinction to make is this of individual versus class. As we mentioned, class represents a set of individuals or instances with common characteristics. So, in our music data example, John Lennon is an instance of the solo artist class, while the Beatles is an instance of the band class. Well, it can take time to build a skill to know what to make a class and what to make an instance. But in such a case, the class is a more generic abstraction of the individual it represents. An individual or instance, it's a more specific type of thing. So it's an instance of a class. In addition, another important ontology concept is this of property. Properties represent relationships, and we have two types of properties. Object properties, defining relationships between individuals, or else called instances, and data properties, defining relationships between an individual and the literal, such as a string, a boolean, an integer, etc. So in our music data example, we can see that a member is a type of RDF property. In this case, this is an object property, and it defines the relationships between an individual of a band and an individual of a solo artist. On the other hand, the property date is an RDF property and of type Datatype, and it basically defines the relationships between an individual belonging to class album and the literal, which is in this case, it's an XSD datetime. Properties can also be organized in hierarchy through the RDF subproperty of term. And as we can see here, track can have subproperties as a single track and an album track. So we covered a lot of ground with regards to the main ontological concepts and examples there. But how do the ontology models and these concepts correlate to relational models? A lot of data come from the relational world, but how do the two words correlate? A table generally represents a class in an ontology model, and then a row in a table would basically represent an instance or individual of a class. The properties correspond to column names, and the cell values will correspond to nodes, literals, and individuals that the node is connected to. Now, if you want to know more on how to turn relational data to a knowledge graph and represent with an ontology model, you should check the training on the virtual graphs. At last, it's important to talk a little bit about naming conventions for the ontological concepts definition. In general, for classes, the local name starts with a capital letter. So for our music data example, we would write the class album with an A capital letter. Now for properties, object or data type, the local name starts with a lowercase letter. So in the case of track property, we will write track with a lowercase t. To summarize the ontology concepts notation, we use rdf type term to state that the data resource is an instance of a class. We use rdfs class or owl class to state that something is a class. Both are supported by Stardog, but consistency is recommended. And we use rdf property and owl object property and owl data type property to state properties. At the end, we can also state class and property hierarchies through the terms rdf subclass of and rdf subproperty of. So let's look into some practical considerations. These include things such as naming scheme, ontology modularity and ontology layering, ontology versioning, and unit testing and debugging. So with regards to the naming scheme, any scheme would actually work as long as this is consistent, and different patterns such as capitalization and delimiters are allowed, suffix or prefix conventions could be used. Singular is recommended versus plural, and you should also try to use annotations instead of overloading the names in order to improve clarity and avoid misuse of terms. Another important aspect is modularity. A single monolithic ontology is very hard to maintain, and on the other hand, it can affect the performance of your knowledge graph, but also of your performance of your queries in the future. You should try to divide the domain into some modules and therefore create separate ontologies with separate namespaces that declare the definition of these subdomains. Also, it's recommended to reuse and share terms between the ontologies. With regards to ontology layering, what's important to understand is that ontologies could be defined to represent different layers of knowledge representation. So we could have upper ontologies defining more general knowledge, we could have middle layer ontologies defining shared domain knowledge, and then we could also have more specialized lower ontologies defining a specific domain knowledge. Another aspect that is important for ontologies, as with software artifacts, is ontology versioning. You should use a version control system, and you should be able to semantically version your ontologies. The version ID should be structured and be meaningful, and should be able to be changed according to well-understood rules. Semantic version specification is a good proposal to be using for ontology versioning definition. So semantic versioning basics are as follows. A version ID is in the form of XYZ, where X, Y, Z fields are integers. The X field is declaring a major change, the Y field a minor change, and the Z is a path. Then additional labels can be appended to the version ID as needed. The semantic versioning principle is as follows. Given a version XYZ, you can increment the major version X when you make incompatible changes, the minor version Y when you add functionality in a backwards compatible manner, and patch version Z when you make backwards compatible bug fixes. So versioning in null is more or less using the unique identifiers, the unique IRIs of the ontologies, and optionally, you can have a version IRI in addition to the ontology IRI. In cases where the ontology IRI is unique, then we can go with that without necessarily having a version IRI. In cases where we have both ontology IRI and a version IRI, these pairs we should make sure is unique. So what is important is the uniqueness of the IRI and the version together. Now, with regards to testing the ontologies, similarly to software products, we can check for logical errors and create tests to check unsatisfiable classes or inconsistent instances. We can also check things such as inspecting the inferences and detect any unintentional inferences. And at last, we can develop a set of unit tests and treat the ontology model as a program effectively. And unit tests can be developed as Sparkle queries, where we have a number of expected results to be expected as part of the Sparkle query results. And in this such case, basically check an expected schema behavior. But we can also use SACL shapes constraint language to define shapes that make the test more declarative. We have covered a lot of ground on the theory of ontology concepts, on the development process of an ontology model, and practical considerations around this. So let's put things in practice. There are a number of ontology development tools and editors in order to be able to create and develop your ontology model. Stardog provides Studio Models Editor, which should be your primary modeling tool to go. Another proposal is ProtoZ, which is a free open source ontology editor and framework. And models created by ProtoZ are compatible with Stardog and basically can be imported and be used along with your knowledge graphs. So next, we're going to use Stardog Studio Models Editor to walk you through the fundamentals of building a music ontology model using the music data example. A little bit about the music data example and the key concepts defined here. So as we can see in the RDF schema representation here, we're going to define a number of classes such as album, song, artist, songwriter, etc. And then a number of relationships and attributes with regards to these classes. It's time for the demo and for creating your first ontology model using Stardog Studio Models. Before starting the demo, let's do some preparation. So step 0, as we have already mentioned in the ontology development process, is to identify the data requirements and key concepts to model in your ontology model. Now, looking on the music data example, we realize that the critical entities to model there are classes such as person, artist, solo artist, band, album, song, and songwriter. And then there are property relationships such as member of band, track and date of album, length and writer of song. The first step would be to create a music database into Studio. So we should be able to be set up with Stardog Server and Stardog Studio in order to be able to create a first instance of your new database that will hold your ontology model. The next step would be to go through the Models Editor feature in Studio and start creating a new model. Creating a new model requires definition of model name, a name graph where your ontology model would be maintained and stored, and then a prefix and an IRI, which is unique for your ontology model. The next step is to start adding some key classes. So in this case, we add the first class, which is artist. We add a label for that, and we also add the type of class, this being a null thing. In addition, we can add an additional class as a solo artist, and we can go on populating all the different classes through the Classes Studio Model Editor tab. Next step would be to start adding relationships. First, we can add some object properties where we will have to define the domain and range. And we can go further populating all the list of properties and do the same with attributes, which are the Datatype properties. So in this case, we can see an example of date, where the domain is class and the range is date time. We used to do the same for the other Datatype paratype properties we have to populate. And the last part would be to add constraints. Model editors also allows you to add cyclone constraints through the Constraints tab. However, we will cover in detail the cyclone constraints tutorial as part of a separate training session. Here we can see the Constraints tab in the Model Editor tab. And this is a final graph visualization overview of your music data ontology. So let's get started. So in the next part of our training, we're going to create a new ontology model based on the music data example by using the Models Editor of Stardog Studio. So as long as we log into Stardog Studio, then we have to click on the Databases tab, and then we have to create a new database by picking a database name. So in our case, we're going to select Music DB. We set the configurations by using defaults, and then we just click Create. And as we can see, a database with the name MusicDB is now created, and the database status is online. The next step is to hover over the Models Editor tab in Stardog Studio, then select the database MusicDB we just created, and then try to create our first model by clicking Create Model. As long as we click Create New Model, then we will have to provide the model name, the name of the name graph where we would like to store our ontology model, a prefix, and an IRI. So for the model name, we will just pick Music, Ontology, and then for the name graph, we will just use Music, Ontology, graph. And then for prefix, we will just use music. And as the IRI, we will set the default IRI of Stardog, which is http://api.stardog.com. And then we click Create. As we can see, a new model called Music Ontology has been created in our database MusicDB, and it's actually stored in the name graph we have defined. As long as we have created a container for our music ontology model, now we are able to go through the different features here and be able to add new classes, relationships between these classes, attributes, constraints, and even have a text editor view in order to basically add our new features of the model. So we will use the tabs here. So let's try to add the first class for our music data example. We will start with the class artist. So we need to provide a label for that. And then we click create. And basically our first class is created for our music data example. Again, here we need to provide an rdfs label. We can provide a description that is artist description, and then we can also define the parent class. So in this case, that would be allthing, as this class is at the top of the hierarchy. And then we click save. And this first class artifact has been saved in our model music ontology. Then we can keep adding new classes by using the plus sign. So the next class we're going to add, it's going to be solo artist. We click create, we provide an rdfs label. And a description. And then in this case, the parent class is artist. So then we type artist and the class name will appear up, and then we hit save. And as we can see here, solo artist shows as a subclass of artist already. The next class we're going to add in our RDF model, ontology model, is band. So band is also a subclass of artist, so we will provide the label for that, an rdfs label and a description. And the parent class again is artist. And we hit save. In a similar manner, we can add the rest of our classes here. So we can add album class with a label and a description. The parent class here is allthing, and then we hit save. And then we continue with class song. The label and description. The parent class here is again allthing, and then we hit save. And we can also see the class song here in the list of classes. The last class to add is songwriter. We add the label again. And a description. And then the parent class here is going to be album. And then we hit save. So as long as we have created the full list of our classes for our basic ontology model for music data here, the next step is to identify the relationships between classes. So by introducing new relationships. The first relationship we're going to introduce is the relationship artist. With label artist and a description that describes the relationships between two classes, the album class and the artist class. So basically, this is a relationship between album and artist class. So basically we say that an album has an artist. So the domain class here is album, and then the range class here would be artist. And then we hit save. So the next relationship we're going to introduce is one between the classes band and solo artist, and it's the relationship member. So basically, if we provide a label for member and a description for that, so what we understand here is that this relationship, or as we call it object property, ties the classes band and solo artist. So we say that basically a band has members and solo artists. So the domain class here would be band, and then the range class here would be solo artist. And then we can save this new relationship as well. Similarly, we have the relationship writer. We provide a label for that and a description. So basically, the writer relationship property describes the relationship between song and songwriter. So a song has writer, some songwriter. Therefore, the domain of this relationship object property would be song, and then the range would be songwriter. Then we can save these relationships as well. Now, the last relationship we're going to add here is track. So we also provide the label for that and a description. So this is a relationship between album and song classes. So basically, an album has a track, some song. So the domain here is the album class, and the range would be song class. And we hit save again. So till now we have defined the full set of classes and relationships for our model. And the next part is about defining attributes. So attributes define the type of properties that range to a type of text, such as a Boolean, or a date, or an integer. So in our case, in our model, we need to define a date property or attribute, which is a data type property. And we provide a label for that and a description. So as we can see, this is an attribute called date defining the album date. Therefore, the domain would be on album class, and the range would range on date. And we hit save. In a similar fashion, another attribute we need to define is the length of a song. So we have to define a label again for that and provide a description. So we can see that we use this attribute to define the song length. Therefore, the domain for this property will be song, and its range will be basically a decimal. And then we can hit save. So now we have defined the full set of classes, relationships, and attributes for our model. And as we can see, there is also a constraints tab. So it is possible through our models editor to define constraints using SACL constraint language and be able to create a validation report regarding with the model. But this is going to be part of a separate training on SACL and data quality validation. And then at the end, I would like to showcase you the text editor version of the model we have created here for the music data example. So we can see here that all the classes are defined together with the properties, object properties, but also data type properties such as date and length. And basically, this is the full process for creating a simple ontology model. That concludes the Stardog Academy training on modeling, building a data model for your enterprise knowledge graph, where we reviewed how to build a data model using Stardog Studio to support your enterprise knowledge graph, fundamentals of data models and data modeling as a process, basics of existing types of models including ontology models, the process of successful ontology model development and associated best practices, foundational concepts of ontology models illustrated through examples, including an overview of existing modeling standards and language representation. Thanks for following along, and if you have any questions, please review our frequently asked questions page or head to stardog.com/docs for additional information. Thank you.